All right, let's jump right into this explainer and completely shatter a myth about how we measure the success of artificial intelligence. We live in a world where AI algorithms are just quietly running huge chunks of our lives, right? They're diagnosing diseases, filtering our inboxes, screening resumes, even approving our credit cards. And whenever we hear about these cutting-edge systems, the very first buzzword thrown around is usually accuracy. I used to think accuracy was the absolute gold standard. It just makes intuitive sense. But it turns out relying on that one single word can be incredibly misleading. Because what if I told you that a remarkably high accuracy rate could actually be hiding a completely useless or even incredibly dangerous AI model?
So picture this. Imagine a revolutionary new AI screening tool hits the market, and it boasts a 99% accuracy rate for detecting cancer. If you read that in a headline, you'd probably think, wow, we need this in every single hospital right now. 99 times out of 100, it gets things right. It sounds like a total medical miracle. Investors would literally be throwing money at it. Doctors would be clamoring to use it. With a 99% success rate, seriously, what could possibly go wrong?
Well, here's the catch, and honestly, this completely blew my mind the first time I learned about it. Let's just walk through the math together. Say you have a real-world data set of 1,000 patients. In this specific group, exactly 10 of those patients actually have cancer, while the other 990 are perfectly healthy. Now, if an AI model is just lazily programmed to blindly guess healthy for every single person who walks through the door, it'll be correct 990 times out of 1,000. Mathematically speaking, it is technically 99% accurate. Yet, it completely missed all 10 of the sick patients. The model essentially cheated the test, just by exploiting the fact that the disease itself is rare. It's entirely useless as a diagnostic tool, despite its glowing report card. This perfectly highlights why accuracy alone just doesn't cut it when dealing with imbalanced data. To see past this illusion, data scientists have to peek under the hood and use a much better tool to expose exactly where a model is messing up.
Section 1. Meet the confusion matrix, the ultimate lie detector.
Okay, so we start by breaking every single prediction down into 4 specific, highly revealing buckets. First up is the true positive. This is the absolute ideal scenario, where the model successfully spots the exact thing it's looking for. Data scientists call this a true positive for a very literal reason. It's true because the AI was completely correct in its guess, and positive because it spotted the presence of the condition it was hunting for. The patient has cancer, the model actually predicts cancer, and life-saving treatment can start right away. It is a massive win.
Next, we have the true negative. This represents a correct prediction of the absence of a condition. So the patient is healthy, the model confirms they're healthy, and everyone goes home happy and relieved. Following that same logic, it's true because the AI was right, and negative because the condition was, thankfully, not there. So far, so good, right? These first 2 categories represent all the times our AI is doing exactly what we built it to do. But, as we know, AI isn't perfect, and this is where things get really interesting. Enter the false positive, or what's known as a type 1 error. This happens when the system triggers a false alarm. Think of a false positive kind of like your car alarm going off at 3 a.m. just because a strong breeze blew a leaf past the sensor. It is loud, it's annoying, but ultimately, your car is totally safe. Translating that back to our medical AI, imagine a perfectly healthy person being told by a machine that they're sick. It causes a ton of unnecessary stress, maybe some invasive follow-up procedures, and wasted hospital resources. It's super frustrating, sure, but usually it's a mistake we can recover from with some more specific testing.
And now we reach the most critical and honestly terrifying category. The absolute most dangerous outcome is usually the false negative, the type 2 error. This is when the AI gives a completely clean bill of health while a severe disease is just going completely undetected in the background. The patient is actually sick, but the computer confidently says, nope, you're fine. In medical diagnostics, a false negative can literally be a matter of life and death, simply because a critical, time-sensitive window for treatment might be completely missed, all because the doctor trusted the machine.
When you map these 4 categories out together, it just makes so much sense. It brilliantly illustrates how true positives, true negatives, and false negatives form this foundational grid we call the confusion matrix. By plotting the actual real-world classes on one axis and the AI's predicted classes on the other, you get this completely transparent X-ray view of exactly how your model is behaving. It forces reality to sit right next to the AI's prediction in a way that a single accuracy score just never, ever could.
So the crucial takeaway here is that by plugging real test data into this matrix, like let's say a test on 100 patients gives us 40 true positives, 45 true negatives, 5 false positives, and 10 false negatives, we finally have the exact numbers we need to calculate the metrics that actually matter. Instead of one deceptive little accuracy percentage, we've got a comprehensive dashboard.
From this one single table, we can generate a whole suite of performance indicators that tell us the true, unvarnished story of our AI. And once you have your matrix fully populated, you run into this fascinating tug-of-war between two competing priorities. Because once you move past basic accuracy, you gotta decide what kind of model you actually want to build.
Moving on to Section 2, the great debate, precision versus recall.
This brings us to precision and recall, which essentially function like a mathematical seesaw. Precision focuses purely on the quality of the alarms the AI sounds. Basically, if the AI confidently says this is positive, how much can you actually trust it? Recall, on the other hand, which is also known as sensitivity, focuses on whether the AI managed to cast a wide enough net to catch every single real threat. Like, out of all the actual positive cases hiding out there in the real world, what percentage did the model successfully find? And because it's a seesaw, usually, tightening up your system to improve one of these metrics means you're mathematically forced to sacrifice the other.
Let's see how this plays out with a practical, everyday example, your spam email filter. In this scenario, false alarms are highly disruptive. If your spam filter is way too aggressive and it marks a legitimate, super important email from your boss as spam, that is a huge problem. That's a false positive. So for spam filters, you want extremely high precision. You want to be absolutely positive that what goes to the spam folder is actually spam, even if it means sacrificing some recall and letting a few harmless emails from a Nigerian prince slip right into your main inbox. But what happens when your problem requires a really delicate balance? What if you need both high precision and high recall without leaning too far in either direction? How do you compare two completely different models when one is better at precision and the other rocks at recall?
Which brings us to Section 3, the balancing act, the F1 score. This is where a super clever piece of math called the F1 score steps in as the ultimate peacemaker. Instead of just taking a simple, lazy average of precision and recall, it calculates what's called the harmonic mean. Now, why does that matter? Well, think of the harmonic mean like a really strict teacher giving a final grade on a group project. If one partner does 100% of the work and the other does 10%, a simple average might say the group gets a 55%, technically a passing grade. But the strict harmonic mean teacher heavily penalizes that imbalance, and the group fails. The F1 score will only be high when both precision and recall are pulling their weight, giving us a single, incredibly reliable number that summarizes overall balanced performance.
Applying this to a real-world test of 1,000 emails, just look at the stark contrast we uncover here. In a test resulting in 300 true positives, 50 false negatives, 20 false positives, and 630 true negatives, you could proudly march into your boss's office and boast a total accuracy of 93%. It sounds phenomenal on paper, but the true hero here is the F1 score. It's the specific balance of correctly catching 300 spam emails while only falsely flagging 20 normal emails that truly proves this model's worth in the wild. It shows a remarkably strong F1 score, making it highly reliable without being overly disruptive to the person actually using the email.
Now for Section 4, the big picture, ROC curves.
So far in this explainer, we've assumed a strict yes or no outcome from our AI. It's either cancer or healthy, spam or normal. But in reality, AI models actually output probabilities. They'll say something like, I am 90% sure this is cancer, or I'm only 40% sure. We humans are the ones who have to set the threshold to turn those probabilities into a strict yes or no. Think of the threshold like the sensitivity dial on that car alarm we talked about. Dial it way up and you catch every single car thief, but the alarm goes off every time a heavy truck drives by. Dial it way down and you sleep peacefully through the night, but, well, your car might actually get stolen. The ROC curve, or Receiver Operating Characteristic Curve, basically maps out every single click on that sensitivity dial. It plots the true positive rate against the false positive rate across every possible threshold between 0 and 1. The absolute holy grail here is a curve that bows really closely to the top left corner. That means high recall with very few false alarms. But a diagonal line straight down the middle, that just means your incredibly expensive AI is essentially flipping a coin.
Ultimately, diving into all these mathematical metrics reveals something profoundly human. When we build or evaluate AI in the real world, the math actually forces us to step back from the raw code and answer a deeply ethical question. Which type of mistake are we more willing to accept? Are we willing to endure a few stressful false alarms if it guarantees we catch absolutely every single instance of a deadly disease? You see, understanding these metrics isn't just some fun exercise for data scientists. It's about deciding what values we want our automated technology to prioritize in our society. So the very next time a tech company boasts that their shiny new AI is 99% accurate, don't just applaud. Ask them, what about that 1%?
And who exactly pays the price when it gets it wrong? Thanks for joining me on this explainer. I'll see you in the next one.